Hi, everybody. We're going to get started in just a couple minutes. We're going to try to start right at 1 o'clock. Right now, we're letting a bunch of people into the webinar, so just sit tight and we'll get started in just a couple. We're going to get started in just a couple minutes. If you are having any problems, please type your question or comment right into the chat box, and we'll try to get that addressed. But everyone is muted, so please use the chat box. Okay. Okay, I think we're going to go ahead and get started. All right, well, good afternoon, everyone, and thank you for joining us. My name is Chris Vonamy, and I am the Deputy Director for the DuPage County Stormwater Management Department. And we are here today for a webinar involving trees and water-sensitive urban design. Where we will explore the key factors to sustainably reduce stormwater runoff and improve water quality through the effective use of trees. This is a free webinar, and 1 PDH or professional development hour will be available. We have several of these workshops throughout the year. The Illinois Environmental Protection Agency requires this training under the National Pollutant Discharge Elimination System program. So we are encouraging all governmental staff, including stormwater, public works, and transportation staff to view these. And again, one PDH will be available for your participation. If you do have other staff that cannot attend this afternoon, the webinar is being recorded and the presentation will be made available for viewing at their convenience. We will email the link with this information shortly following the program. Before we start, I just want to throw out a couple thank yous. Thank you to Mary Mitros. Mary is our Stormwater Communication Supervisor. She helped organize the webinar. I'd also like to thank the Conservation Foundation. They are our partners for all of these workshops, specifically Jan Rail. She is the DuPage County Program Director for the Foundation, and she helped line up our speaker for this afternoon's program. Finally, once again, I'd like to thank all of you for joining us. Just a real quick public service announcement. With COVID cases increasing within the state and around the country, We hope that everyone remains safe and healthy during these times and continues to practice good hygiene, washing your hands frequently, social distancing, and wearing a mask in public. If you do feel sick or ill, please isolate yourself or quarantine to prevent the further spread of this coronavirus. Just a couple other quick notes. I hope that everyone enjoyed a great Veterans Day holiday yesterday. I'd like to thank all of the brave men and women who have served in the United States Armed Forces over the years and who are currently serving now. You know, there is a very good reason why there are no knock-knock jokes about the United States of America. And that's because freedom rings, my friends, freedom rings. All right. We have a great speaker and presentation to share with you this afternoon. We have Shane Carpani, from Green Blue Urban. Shane will tell us about the effective uses of trees to manage stormwater and improve water quality in urban settings. But before I turn things over to him, I do want to remind everyone that you are muted. And so if you do have questions or comments during the presentation, please type them into the chat box and we will relay those on to Shane at the end of his presentation, and we'll get to as many of those questions and comments as time will allow. So with that, I'm going to turn things over to Shane. Shane has been with Green Blue Urban for almost six or 7 years now. He is a consultant there with Green Blue Urban. He attended Athabasca University in Canada, where he studied marketing. And currently, Shane works with landscape architects, civil engineers, and other industry professionals to increase urban tree planting success and to improve stormwater management sustainability on projects across the Midwest. He uses his passion for green infrastructure to help landscape architects, civil engineers, and other related professionals create more sustainable cities where people want to live, work, and visit. Shane speaks frequently at industry conferences, lectures at universities and colleges, and consults with municipalities to increase urban tree planting success and low-impact development practices. So with that, Mary, please turn the screen over to Shane, and he can share his presentation with us.
All right, my screen should be up. Can you confirm that, Chris?
Yeah, we got it.
Excellent. Great, excellent. Well, thank you very much, Chris, for inviting me to speak today, and thank you all for joining. I'm absolutely thrilled to be with you today to speak about a topic that's extremely important to me. Here at Green Blue Urban, we work with civil engineers and landscape architects every single day to create environments in which trees can thrive while sustainably managing stormwater. And that's what we're going to talk about today. So the interesting thing about working with landscape architects and civil engineers is that these are very interesting, very different practices, if you will, that don't, are on the different sides of the spectrum of what Green Blue Urban work with. So we work with trees and stormwater management and combining those two things together. So sometimes Green Blue Urban like to think of ourselves as that collaboration that connects trees with stormwater management, or even you might say landscape architects with civil engineers. So by the end of this presentation, I hope that both your knowledge for trees and your understanding of the benefits that urban trees can provide us. Those are the kind of things that I'm going to be speaking about and what I'd like you to take away from this session. There will be plenty of time for Q&A at the end. So as already mentioned, if you have questions throughout, please don't hesitate to throw them in the chat box there, and I will address as many as possible at the end. So we're going to talk about three primary functions here. Number one is urban tree planting system. So how we accomplish a healthy urban tree in a downtown city environment. So this is, before we can even talk about stormwater management, we need to talk about how to accomplish a healthy tree, because we're not going to get bioretention benefit out of a tree unless that tree is healthy. So we're going to talk about that, how to accomplish that while protecting our built infrastructure. And then once we realize that we will then move into the stormwater aspects of how we integrate stormwater management into those types of systems. So the benefits of urban trees, very oftentimes these are understood purely as an aesthetic or a beautification benefit that trees provide any given area, whether it be a streetscape, whether it be a plaza area, or whatever the case may be. But there's a lot more than just beautification and aesthetics that trees provide. And the second most important one, as we can see here from this study that was done in Indiana, is the second most important thing is stormwater management. So 31% of the benefits provided by trees, and these are economic and environmental benefits, are being provided through what they can do for stormwater management and the sustainable management of stormwater. And we're going to talk about that today. Everything from evapotranspiration to interception, the canopy interception of how the tree collects the stormwater, what it does with the stormwater, increased infiltration, phytoremediation, and different elements in which trees actually accomplish that kind of benefit. But first, we'll start with this statistic, and this is going to help put it into perspective, because this here shows that for every 5% of canopy cover in an urban area, stormwater runoff is reduced by 2%. So every increase in 5% of canopy cover is a reduction of 2% in stormwater runoff. And this is just factoring in the rainfall that's actually landing on the canopy or the leaves of a tree. This isn't even taking in runoff that we're actively channeling into a bioretention tree pit, which we will discuss momentarily. So with that canopy interception, of course, the larger the tree and the more mature the tree, the more stormwater it's going to be able to intercept, and the more stormwater it's going to be able to reduce through uptake of it through its root system as it takes that stormwater up through irrigation. And we'll talk all about this in a bit more detail. Looking at some further numbers here, 880 cubic feet of a engineered bioretention tree pit system can attenuate over 1,400 gallons of stormwater. So this is kind of putting into perspective how much stormwater these engineered tree pit systems can actually manage. So we've worked on projects where through the use of these kinds of systems and designs, we are managing 100-year storm events with no runoff from the site. So huge amounts can be accomplished through the use of this. Now, why do trees fail? So we talked about, in order to take advantage of those benefits, we need healthy trees. Well, why is it that most trees in urban areas are not healthy? And there's a few factors that come into play in relation to that. And the first of which is compacted soil. So not having an adequate volume of uncompacted soil is probably the number one cause of premature mortality in urban trees. So there's no rooting volume for the trees. There's not enough space for the tree roots to establish below ground without damaging surrounding infrastructure. And we're not managing the tree roots into intended rooting areas so that they're not damaging utilities or paved surfaces or building foundations or other built infrastructure that might be around. So we increase the amount of uncompacted soil, and we're increasing both the rooting volume for the tree and therefore the mature rate and the canopy diameter and size of that tree, as well as the infiltration and the volume of which the tree, the area of which, the attenuation area that we have to hold stormwater. So the more roots and the more canopy, the more stormwater these trees will be able to manage. So imagine how to accomplish that in an urban areas. Think of these trees here lining a streetscape or dotting a pedestrian plaza area. How do we provide for this kind of a rooting environment underneath that hardscaped area? That's a lot easier said than done in an urban environment where we've got utilities and building infrastructure that's competing for that space. So that's really where the root space arbor system comes into play, in this engineered system that allows for the marrying of the tree with the built environment. So bringing the best of both worlds and allowing that tree to coexist in an urban environment and thrive and reach maturity, while ensuring that there's not going to be any built infrastructure damage as a result of the tree maturing. So how can we better utilize trees for stormwater management? First, we're going to talk about planning, and then the different design considerations that we have to consider when designing trees. So we're going to talk about water, the way in which trees manage stormwater in terms of both quantity, so reduction of stormwater quantity, and then improvement of the quality of the stormwater that there is. And then, of course, there's other amenity and biodiversity benefits that trees provide as well. So these are the components that we're going to take a look at. These are the considerations, if you will, that we need to make when designing trees into an urban landscape. If we tick off all of these elements here, we are assured to have a tree that reaches maturity in an urban environment. And number one, as I mentioned already, is uncompacted soil. If we don't have enough soil volume, uncompacted soil volume for the trees, they're simply not going to reach maturity. And the most cost-effective way of achieving or accomplishing uncompacted soil underneath a hardscaped surface is through the use of a pavement support system or a soil cell, like we're seeing on the screen here, the root space system. This is a structurally engineered system that is manufactured from 100% recycled plastic. It's H20 rated, so it can be under fire lanes and roadways, not just pedestrian areas. And this system assembles to provide 97% uncompacted soil, or 97% void space. So we fill this system with healthy uncompacted soil. The system itself holds up the surface, and then it's full of healthy uncompacted soil that can be used for tree root growth and or stormwater attenuation. And here we can take a look at some in situ case studies, if you will, of looking at uncompacted soil volume versus compacted soil. So trees on the left in both of these photos are planted in uncompacted soil versus the compacted soil of the trees on the right. And we can see, of course, how much better the trees in uncompacted soil are faring. The amount of soil that any given tree requires in order to reach maturity depends on a couple of things, primarily the species of the tree and the canopy diameter of that tree at maturity. And it can range anywhere from 300 cubic feet to over 1,000 cubic feet per tree in order for that tree to reach what we would call its species potential. Now, bearing in mind these numbers are for individual tree pits, the most cost-effective way to achieve high volumes of soil for trees is when we link tree pits together or connect them together in a linear connected fashion. And we'll talk about that a little bit further on. The thing to understand, of course, is that not all soil volumes are created equal. There are several different urban soil planting or urban tree planting options out there. And before the advent of soil cells, the most popular one was structural soil. So we could see here, Green Blurbin invented the world's first soil cell in the late 1990s. You can see a controlled monitored study here at Bartlett Tree Labs in Charlotte, showing the use of all of these different systems. And you can see after just 1 year, the growth rate provided by the soil cells and how much higher those growth rates are in the trees and soil cells. And of course, that's because structural soil is a combination of 80% 80% gravel and 20% soil. The 80% compacted gravel is what provides your structural stability to hold up the surface. And then it's got 20% soil mixed throughout that gravel that provides growing medium. Whereas the soil cells, like I talked about before, we're using only 3% of that excavated area to hold up the surface with that root space system, and 97% of that area is usable soil. Here, this is after the study concluded at 3 years. You can actually see they air spaded out the soil to expose the tree roots, and you can see how much more root colonization there was from the tree in the tree in soil cells, as you can see here. So as I mentioned here, structural soil is 80% gravel. So these large gravel here, you can see representing that. And then the 20% soil that's mixed throughout the voids of that gravel. This is showing the comparison. So the blue outline that you're seeing here and the red outline is the exact same soil volume. So the blue outline is the structural soil layout, providing 600 or providing 120 cubic feet of soil. And that red area here is the soil cells, providing that same amount of soil, but with less excavation, less labor, smaller area, and providing that same soil volume. So as mentioned, the system is manufactured from 100% recycled plastic. You can see the system in its use here underneath the vehicular parking area. Here we can see a bird's eye view of the installation of the system. Very modular and versatile system, able to be configured in any kind of shape and size. We can see this is actually a pedestrian plaza area that's separating a parking lot from a shopping mall area. You can see the openings here where the tree root balls are going to go. So they're assembling this system out, leaving openings where the trees are going to go. This whole thing will be filled with soil. A surface will be put on and the trees will be planted in the opening. This particular one has a permeable paver surface above it, allowing for percolation through that permeable paver surface into the system to allow for attenuation within the soil volume and tree uptake through the root system as the tree takes that stormwater up through irrigation. Here we can see some of the common depth profiles ranging from 19 inches to just over 4 feet in depth, depending on different situations and scenarios. It's very easy to work utilities into the system, whether they be new utilities or existing utilities. Here we can see the system being filled with soil, very easy to fill with soil. And one of the important things to understand again with this system is that this is being filled with healthy, uncompacted soil. There is no structural blends or proprietary elements. Any good planting soil can be used inside this system. And as I mentioned already, it is H20. So the system's under roadways, maximum vehicular areas with minimal surface above it. And you can see here even the ease and ability of construction equipment to drive right over top of the system without even a surface above it. So here we can see that with as little as 8 inches of surface, the system is H20 rated for maximum vehicular traffic. So we'll take a look at stormwater now that we've talked about some of the elements that we need to be thinking about when in order to have that healthy tree. We'll take a look at the stormwater side of things here because we want to take that stormwater, channel it into this engineered tree pit system to use that soil to attenuate the stormwater and allow the tree to take up that stormwater. So this short animation here is kind of going to show the basic function of the system. In a rainfall event here, we'll see the different ways in which we can bring stormwater into the system, whether it be through a curb inlet, as we're seeing here, into the system through a catch basin or sediment separator and distributed throughout the system. It could be through a linear drain or a trench drain, as we're seeing around the tree there. That linear drain could also be along the back of a curb of some sort. It could be through the arbor vent inlet, as we're seeing there. As number 3, or it could be through a permeable paver surface, as we're seeing right here. We could allow that water to percolate down through a permeable paver surface and into the system as the previous example, installation example we saw, or it could be through another version of pervious surfacing like arbor, like a resin bonded aggregate or decomposed granite of some sort. Regardless of the way in which stormwater enters into the system, it's evenly distributed throughout the soil profile for attenuation and root take-up, and any excess is drained out through a drainage layer below the system, tied into the storm system, and infiltrated into surrounding groundwater depending on site conditions. At which point, of course, that discharged stormwater that we have is significantly cleaner and significantly better quality than when it entered into the system, because the system has used the soil inside the system and the tree to filter out nitrogens and phosphorus and different materials like that. So this chart we're seeing here is a look at that quality improvement of the system. What we're looking at here is total suspended solid removal, total phosphorus removal, and total nitrogen removal. And this is the comparison of the bioretention tree planting system to a rain garden, so a more traditional green infrastructure application of a rain garden. And the top dark green line of each is the target removal rate. The middle green line is the removal rate achieved with the rain garden, and the bottom light green line is the removal rate achieved with the bioretention tree pit. So that you can see in every instance that the tree actually outperformed the bioretention tree pit actually outperformed the rain garden, all with the added benefit of the reduced maintenance. So because a tree doesn't have the same level of maintenance involved that a rain garden or a bioswale has, we can really bring the ongoing costs of the BMP to a much more manageable standpoint. And of course, in addition to the reduced maintenance of the best management practice, we also have the maximization of real estate. So because the system is all below a hardscape surface other than the tree pit opening or the tree planting opening itself, we can maximize real estate or surface for parking, sidewalk, whatever the case may be, versus the otherwise underutilized real estate of a rain garden or a bioswale application. Here we can see a tree planted in the system. This is about 15 or so years after the tree was planted. What we're seeing here, this photo was taken during a rainfall event. What we're seeing here, number one, is the dry spot under the tree that's showing the canopy interception that this tree is providing. But this tree is managing a lot more stormwater than just what's landing on its canopy. It's a little bit hard to see in this photo, but if you can see my cursor, where my cursor is pointing out here, this is a stainless steel, a 4-inch wide stainless steel linear strip drain right underneath where this young man in the gray sweater is walking. And that linear strip drain is taking the stormwater runoff from the front of this building into that linear drain and distributing it to the root space system below. So this one tree is managing a significant amount of stormwater in this outdoor shopping mall area. And of course, we distribute that stormwater through a network of distribution pipes throughout the soil profile. Here's a project in Madison, Wisconsin, showing the use of the system at the Hilldale Shopping Center in Madison. And we're taking the stormwater and distributing it throughout that piping network. Here we can see that linear drain a little bit closer up. This is a common application, whether it be on the back of a curb, along a parking lot area, adjacent to a pedestrian plaza area like we're seeing here. And we can bring that stormwater in and distribute it throughout the soil profile. This particular linear drain here has a shutoff on it so that the system can actually be shut off during the winter months, so that we don't get the de-icing salts that they're using on this surface into the tree pit area. So during the winter months, the stormwater is bypassing the bioretention tree pit area and going straight into the storm sewer. And during the spring, summer, and fall months, when we're not using de-icing salts, all of the stormwater is entering the tree pit system. Looking at a few details here, we can see a high capacity bioretention application here. This is a standard cross section showing one of those applications. Here we can see a road median with a catch basin in a plan view showing stormwater entering. It would be entering through this catch basin here in the roadway and distributing throughout the distribution piping network that we can see. Sometimes we might have a layer below that we're using for stormwater storage, and then a layer above that's full of soil for growing median for the trees. Lots of different ways we can look at designing these systems depending on the goals of the projects and the specifics of the nature that the nature of the project and the goals at hand. Here we can see a parking lot application where through the orientation of the tree pit opening and that what we call a diamond tree pit opening, we can maximize the use of the system without even losing any parking stalls. As we can see here, we can still maximize the full use of parking and real estate while still getting the benefits of the system. So from a development perspective, this can really show how we are still getting our bang for buck, if you will, from a real estate perspective, while still meeting some of these requirements that there are. Here we can kind of see the chart showing the flow of that, depending on whether whether there's a bypass or not, what happens specifically with that stormwater. And these modules can also be used for stormwater storage. So when we're not planting a tree in them, they can be left void of soil and wrapped in a membrane, whether it be a permeable membrane for infiltration or an impermeable membrane for storage or detention. And you can use the system as an alternate to a more traditional dry well or other kind of detention system. The benefits of using this system for that application is that because of the strength of the system, it can be very close to the surface. And because of the 97% void space, we're really maximizing usable area and reducing excavation requirements. Here we can see the system going in the ground in Evanston as a more cost-effective alternate to a gravel dry well. And you can also use the systems in conjunction with each other. This is a Costco building that utilized a low impact development project in this manner, and they're using the two functions of the system together. So they take the rooftop runoff from this Costco building and bring it into the modules empty, wrapped in an impermeable membrane to store the stormwater, and then they use that stormwater to irrigate the tree plantings along the parking lot. So a very innovative green infrastructure application here at this Costco. So looking at how we bring stormwater into the system, it could be through a permeable surface, whether it be a permeable pavers, whether it be a permeable concrete or asphalt type material. This rendering on the right and photo on the left here is actually at the University of Missouri campus, the Mizzou campus in Columbia, Missouri. And this is a parking lot, linear parking lot that's going along the Dobbs Pavilion there at Mizzou. And there is a permeable paver parking along that with the system underneath it. And they're taking all the runoff from the parking lot and channeling it into that, the permeable pavers, parking stalls there, and allowing that to percolate down into the system for attenuation and tree root take-up. It could also be another kind of permeable surface, like a resin bonded aggregate or a decomposed granite of some sort. I apologize for the banging going on here at the office. I seem to not get the memo about the furnace being replaced today, so I apologize for that. But linear drain, we talked about the linear drain already. Here we can see an application lining the back of a curb, and this is taking the sidewalk runoff from this sidewalk through that linear drain and bringing it into the soil cell system below. A curb inlet, like we're seeing here, bring it in off a roadway. This particular curb inlet is called a curb flow, and it has a closable valve on it. We can see on the background photo there how it's actually closed. And this is, as I mentioned, allowing for the shut off of the system during the winter months, so that we don't get those de-icing salts from the winter entering the bioretention tree pit system. Or it could be integrated inside the catch basin through a gate valve application like we're seeing here. And this is allowing the use of a single catch basin and with a simple gate valve shutoff that allows the system to be shut off during the winter months, so that the stormwater is bypassing into the storm sewer, and during the spring and summer and fall months, that gate valve is open, allowing the stormwater to enter the tree planting system, and only in a very heavy rainfall event where the system is at capacity is it overflowing into the storm sewer. We could also look for bioretention or for pre-treatment purposes, rather, when we don't want unnecessarily have to shut the system off during the winter months. We could look at another type of pre-treatment to remove those de-icing salts and heavy hydrocarbons prior to their entering the bioretention tree pit system. And that can be done through a plug and play rain garden application like this. It's taking those heavily salt saturated water and pre-treating it prior to its entering the tree pit area. So taking a look at maintenance of this system, as I mentioned already, the system is very low in maintenance. We can see there's a couple things in relation to the tree that need to happen, or checking the inlets for the stormwater, ensuring that the inlets essentially, though, as long as keeping those inlets clean and clear, whether it be a catch basin, curb inlet, whether it be a linear drain, whether it be the permeable surface itself, whatever we're using as that inlet, we need to make sure that that inlet stays clean, because if that inlet gets clogged, then of course the system will cease to function. And then there's some tree related things, of course, like debris and pruning the tree, structural pruning of the tree as necessary. And that is quite literally all the maintenance involved in this system. So very low maintenance way of taking a look at some of these bioretention, low impact development applications. So we'll take a look at some case studies now and try and put things into perspective. The Navy Pier uses our system. You can see this is before. This is during the installation of the system. So here throughout, this is just after the installation. So these trees throughout the pier area are using the system. This is shortly after the installation was completed, and these are the trees 2 years later. So the trees are doing very well, even in this completely hardscaped urbanized environment. These trees are thriving as though they're in a forest-like setting through the provision of the system. So we can have trees that are thriving even in the most harshest urban settings when we design for them accordingly. Lancaster, Pennsylvania, we can see a cross section here pulled from the City of Lancaster Standard Detailed. The Lancaster, Pennsylvania is very progressive in their green infrastructure goals. They have implemented huge amounts of green infrastructure throughout the city, and to the point where they are now seeing a reduction in gray infrastructure costs, significant reduction in gray infrastructure capital costs as a result of the benefit and cost savings that they are seeing and achieving through the use of green infrastructure throughout the city. And these kinds of bioretention tree pit systems play a large role in that. Thunder Bay Hospital up in Ontario, Canada. This was a hospital that we worked on that had a large storm pond on site, and they were short on parking, so they wanted to use that the storm pond area for a parking lot. So they used our system underneath the parking lot. So they turned what was a parking lot, or I'm sorry, what was largely a storm water pond area, and turned it into a parking lot, with all the while still meeting the stormwater requirements through the use of the system below it. So this is what we call one of those hybrid systems, where some of the modules are full of soil to provide growing medium for the trees, and some of the modules are empty for stormwater storage. RSM Plaza in Minneapolis, we can see the system used there in a plaza application. Hatcher Road in Phoenix, Arizona, interesting use of the system on a permeable paver parking lot, or a permeable asphalt rather, permeable concrete sidewalk. Front Street in Toronto, Canada, we can see the another one of these linear drain applications along the back of the curb. The River Walk in Chicago this is the River Theater area. This is one block of the River Walk area that our system is being used to support the trees here. And this is also a green infrastructure application that is taking stormwater and channeling it into the system to prevent as much runoff as possible. So see some of these applications you may have been to or walked past, or even had lunch here and not even know what is happening in these areas in terms of the green infrastructure. Pace University in New York City, here we can see a permeable paver application with the root space system underneath it, allowing, this is in a atrium area in the center of the university, allowing for rainfall to percolate right through these permeable pavers to the root space system below. Boston, Massachusetts, this is a really great comparison showing the growth rates of trees in the system. So these trees were planted on the streetscape in 2015. So we can see on the far left there, 1 year after planting, and then 2 years later and 2 years later again, just showing how well these trees are thriving, even in this heavily urbanized downtown Boston area. These trees are doing extremely well as a result of the system. So taking a look at the cost benefit analysis on some of these to get into kind of a bit of the dollars and cents. So Madison, Hilldale Shopping Center in Madison, we'll take a look at here. This is the design here. This is a shopping mall, an outdoor shopping mall. You can kind of see a plan view here of the various trees planted here. This is the design. They're bringing stormwater in, distributing it throughout distribution pipes throughout the system. So taking a look at the cost of this was planted in 2019, so just last year, at an installed cost of just over $9,000 per tree. And it's achieving 610 cubic feet of volume, of soil volume for those trees, or rooting volume for those trees. So at a cost of just over $9,000 per tree, that's all material, installation, everything inclusive. These were providing an environment in which these trees are going to thrive long term and provide all the aesthetic benefit in addition to the shade provision and all the other benefits that this shopping mall wanted, in addition, of course, to this management of stormwater on top of all those other benefits. So site review and installation support, of course, as a consultant in these kind of green infrastructure bioretention applications, Green Blue Urban support with the design and implementation of these kinds of systems, really from start to finish, provide various different resources in also details and designs and cost estimations as well. And there is also a free resource that I'd like to offer everyone today. If you write down that bit.ly link at the top right side of the trees, bit.ly/LID-trees, you will be able to download a free copy of the Trees and Water Sensitive Urban Design Guide that details much of what we've talked about today, goes into a few more case study examples, and details things in a bit more intensive dive, if you will. So this brings the end of the presentation. I might have scaled back on some of the case studies. It looks like we've got plenty of time here for Q&A here. We're about 15 minutes left here, so I'd be happy to open things up, Chris, to you or whoever, whatever moderator is going to field the questions here.
Sure, yeah, great. Hey, great job, Shane. Thank you very much. We do have quite a few questions that have been rolling in throughout your presentation.
Great.
So let me read a couple of these things to you. First question is this system designed for any particular tree species, and are there any common species not compatible with this setup?
Sure, great question. So no, it is not designed for any specific tree species, and it is not specific to any particular species. We have quite literally hundreds and hundreds of different tree species successfully planted in the system. When it comes to species selection, it's not about the system, it's about the surrounding environment in which we're planting the trees. So what I mean by that, of course, is if we're planting a tree next to a roadway, we're going to want to ensure that we're using more salt tolerant species. We're going to be wanting to ensure that we're using more columnar style trees that aren't going to be brushing up against the building front of a building if we have a tight sidewalk and streetscape application. You know, there's different considerations like that when it comes into species selection, but it's not in relation to the root space arbor system itself.
Okay, great, thank you. I know you had a slide in here that talked about some of the maintenance, but a little bit more about the maintenance. Does the system require any long-term maintenance?
Yes, the long-term maintenance is cleaning out of the inlets. So that's I mean, you'll never not have to do that. That's a permanent thing. So if the inlet clogs, you clean it out, or the system is not going to function. And depending on the amount of stormwater going into the system, and depending on what inlet you're using, that can range anywhere from, you know, once every 2 years to as much as once every 6 months. It's really hard to know, you know, without understanding more about the, you know, the runoff volumes and what kind of stormwater runoff we're bringing into the system. But yeah, that's the only maintenance besides perhaps some structural pruning of the tree and watering the tree in a drought situation. You know, say that we have a prolonged drought situation, you're going to need to make sure that that tree gets watered if there's not adequate rain going to the tree. Other than that, cleaning out of that inlet is the only maintenance that is required.
Okay, great, thank you.
Inlets, plural. Yep.
Yeah. One of your slides showed a comparison of trees in compacted soil and uncompacted soil. Is that with the soil cell system, or is that just the native undisturbed soil?
That's a great question. Yep. So those particular ones, if you're thinking of the one that was in Knoxville or Chattanooga, Tennessee, rather, those were comparing the native soil, in essence, that grassed area that the trees were planted. And so you wouldn't use soil cells. There were other comparisons on other slides that did use soil cells. In that particular one in Chattanooga, that was native softscape. You would only use, and this is a good segue to reiterate, you would only use soil cells underneath a hardscape surface. So the purpose of the soil cell is to provide that uncompacted soil volume underneath a hardscape surface, like this background photo that we're seeing here on the current slide. In a softscape area, you would not have soil cells in that area because that soil is already uncompacted and free with the territory, if you will. The nature of a softscape surface is providing that element already.
Okay, great. Thank you. Couple more questions here. Has this system been shown to reduce root girdling?
Sorry, you cut out on me there, Chris. I'm not sure if that was my end or your end, but could you repeat that question?
Absolutely. Has this system been, has this type of system been shown to reduce root girdling?
Yes, absolutely. So it's a very good question. Root girdling typically happens from nursery. So typically when trees are planted in a container grown, when we container grow trees in a nursery, that's when root girdling starts. So really, that's kind of a nursery selection or a stock selection question, and then ensuring that we're selecting quality stock and taking all the necessary steps at time of planting to ensure that any girdled roots are cut back and allowed for, or of course just have open grown trees, or more preferred growing methods at the nursery. But yeah, to directly answer the question, yes, the system is designed in which to not have any girdling roots. The trees have a large volume of soil that they're being provided through the root space system, and the trees grow throughout that system without any girdling nature.
Okay, great. Thank you. This next question looks like a three-parter. Let's
I
see.
like those.
Where does the removed material go? What is the rate of accumulation? And when will the holding area have to be cleaned out?
Okay, so is this in relation to using the modules empty for stormwater storage? I mean, that might be, whoever entered that question, it might be better if they email me directly to the email on here, because that sounds like there's some pretty specific things that you've got in mind there. So just to answer that, I would need to know whether you're referring, it sounds like you're referring to the system without soil in it being used for strictly for stormwater storage. But regardless, if you want to email me directly on the email address provided on the screen here, I can help with that.
Okay, great. That sounds good. What certification is required to install these products?
Great question. There is no certification required. So we provide, we do have a installation video, an online installation video that in some cases for smaller projects, the contractor quite literally just watches a 20-minute video and they're away to the races. We also provide on-site support, so we'll send a consultant to site for larger projects to provide support on that. We also provide pre-installation dry run mock-up installations prior, as well as webinar style sessions with contractors and municipalities and public works departments, where we will review the installation of the system and answer any questions prior to an installation occurring.
Okay, very good. A couple more here.
Sure.
Can frozen water in the stormwater management system damage the cells?
Great question. So no, it does not. The reason for that is a few fold. Number one being because the system is 97% void space, there's room for the expansion and contraction. So in the event, first and foremost, it would be relatively unlikely for much stormwater to get in and enter the system unfrozen, freeze inside the system because of the salt laced nature that most of that stormwater would be in. To that effect, even if that does happen, there's room for the expansion and contraction within that system. When we have freeze thaw issues is because we don't have there isn't that provision of expansion and contraction, which there is in this system. So no, there are no issues. We have the system in winterized climates from Minnesota to Alaska to northern Canada to Finland, Denmark, Norway, and everywhere in between. So.
All right, great. Let's see, what system is recommended for a residential application combined with native plants?
Okay. Native plants as in not trees, I guess they mean. Can participants unmute themselves in this or not?
I don't believe so. I think that would
Okay.
take,
Okay. I was just going to say they could maybe unmute themselves. And when you say native plants, I'm assuming that you mean
like native wetland plants.
Yeah.
Yep.
So typically this system is being used for trees. It's not usually used for planting, shrubs and other kinds of reeds and different plants like that. It has been and it can be. It's just not typically used. When it is used in that function, as a matter of fact, I'm working on I was just working on a project earlier today in Milwaukee that did that. And yeah, I mean, it certainly can be. And depending on the amount of storm water that you're planning on channeling into the system, that's kind of the determination on what type of system or design is applied. Less
Okay.
about the plants, and more about the what we'll be treating.
Okay, very good. With 20% soil, what type of nutrient supplement is required?
So the system is 90. The system is, well, the soil that's going in the system is 100% soil. The 20% soil was in structural soil. So that was a comparison showing how this system is better than structural soil or is an improvement to structural soil. That was just kind of showing how we have taken this further step to improve structural soil. So that's why this system was invented, was so that we could move away from structural soil and into this system. So again, the soil going in this system is 100% soil of a sandy loam classification, is what we would normally say, which is appropriate amounts of sand, silt, clay, and organic content. So essentially healthy planting soil. In layman's terms, healthy planting soil, 100%.
All right, very good.
And I'll just add to that.
Yeah.
The bioretention. Sometimes we might lean more to the bioretention side of a soil if we're looking at bringing storm water. If we're looking at keeping our infiltration rates up, our soil specification might be a little bit more on the bioretention side of things. But then there's a bit of a balancing act that we have to make there. On one side, we want the infiltration rate high enough that we're the percolation rate high enough that we're meeting our infiltration targets. But on the other side, we don't want it so high that the water is flowing through the soil so fast that the trees can't even take it up through irrigation. But that's kind of another topic altogether.
Yeah, and that kind of maybe goes along with this next question. So when using the system with a tree, is it correct to state that the stormwater benefits you mentioned are all water quality? This system does not address water quantity unless you have a separate system that does not include uncompacted soil.
So the quantity aspect that it is managing is through the uptake of water through the tree. So the trees need water to live, obviously. Like you water trees and plants, and they take that storm water up through their root system, distribute it throughout the tree and through evapotranspiration and different elements like that. That is a reduction in quantity. Now, that being said, it's very hard to quantitate that reduction value, which is maybe maybe where that question was stemming from. There are numerous studies on the go right now with different universities across the country and around the world, even many of which Green Blue Urban are a part of, that are looking at that. But it's very hard to quantitatively assess that because it varies so much in terms of, number one, the species of tree, number two, the age of the tree. So different species of trees take up more water, more irrigation than others. The age of the tree, obviously, the older and more mature a tree is, the more water it absorbs. So it varies quite significantly depending on some of those different factors. But yes, from a quality improvement standpoint, it's much easier to quantitate that because it's quite literally sampling the water going into the system and saying, you know, our phosphorus and nitrogen and suspended solids and hydrocarbons were X, 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 and X going into the system. And you have an outlet with an inspection riser that you're testing the water leaving the system and saying when it left the system, they were X, 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 and X, and therefore there was a reduction of X, 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 and X. I'm not sure. Hopefully that answered his question or her question.
I think so. And looks like we have maybe just one more. Have any studies been done of the soil health after it's been in for several years? Wondering about the presence of earthworms, fungus, and other soil inhabitants.
Yep, so that is a really good question. I actually was just sent information on a study last week on one of our, just gonna pull it up here, because it was looking at exactly that, and I'm just trying to. All right, so I'll read a short excerpt here out of a that might kind of help with the with both of the last questions, that the two last questions that we've just had here. So let's give me a moment here. Okay, so the system in turn, the system manages both soluble and insoluble. So there's a couple different ways of looking at to pollution entering the system. I was going to read this out, but I think it's a bit too long. But so there's insoluble and soluble. Soluble metals like aluminum and other chemicals break down into the soil and are taken up by the plants, which is I mentioned the term phytoremediation earlier in the presentation, and that's what that is. That's what the phytoremediation process is the plant material taking up those kinds of soluble metals that are inside that stormwater. Non-soluble metals that don't break down, like iron oxide and other things, that's where the inlet comes in. So that would be filtered out through the inlet, whether it be a silt trap or whatever the inlet might be. And they are cleaned out through the inlet. And other than that, in terms of the long-term effects of the soil, this is, in general, all the studies that we have done, we're looking at like very minimal amounts when it comes in turn to test the soil. We're talking about like parts per billion. We do not have studies that are much more than 5 or so years old, but over 5-year-old studies that we have, we're still looking at pollutant rates that are in the parts per billion. We can't say Green Blue Urban haven't directly been involved in any studies that use our system for significantly longer periods of time than that. So we can't exactly state what it would be like over long term, but over 5-year long study, the pollutant rates are very minimal inside the soil, inside the system. So I'm guessing that what he's asking, or what they're thinking about, is whether the soil needs to be replaced. I wonder if that's where that question was being poised from, about whether it would ever come to a point where the soil inside the system would need to be replaced, and that would not be the case. So
Okay. All right, well, great. Hey, great job on the presentation and great job answering all those questions. I'd also like to thank the audience for those questions. Very good questions and great job answering those. But right now, I think that's all we have time for. So I'd like to thank Shane one more time for his knowledge and experience and sharing those with us. I'd also like to thank all of you, our audience, for joining us this afternoon. We hope you enjoyed and learned a few things from the webinar. We will email everyone a link with the recorded webinar, the presentation, and a PDH certificate. And please look for our future webinars. We're going to take a little break from our watershed webinar series, but we'll start this back up in February. But in December, we will have 2 green infrastructure maintenance webinars, one on December 3rd and the other on December 10th from 1 to 2:30. So look for those. So until next time, be safe and be healthy. Thank you very much and have a great day.